Bismillah ar-Rahman ar-Rahim. Diffusion and osmosis. Diffusion means that the molecules transfer through a layer or an area or without a membrane as a broken pipe where nitrogen can escape from it. This illustration shows how does the gas diffuses through the alveoli and then the capillary alveolar membrane, and then after that to the skin and to the blood, and after that from the extracellular fluid to the cells. So this process is called diffusion. The first law in diffusion is Fick's law, states that at the rate of diffusion of a substance across an area, unit area, as a surface or a membrane is proportional to the concentration gradient, simply speaking. It is applied on homogeneous phase, or a slight modification can occur if it's being transferred from a phase to another phase, as from a gas to a liquid. So we call it at that point, it's proportional to the tension gradient. Tension means the gas in a solution. You see, of course, whenever the gas is more soluble in a solution, the tension gradient will increase and will increase the rate of flow. The blood normally takes around 0.75 seconds to pass through across the alveoli. During the first 0.1 second, there is a complete equilibrium regarding carbon dioxide, you see, but it takes around half of that time for oxygen to be equilibrated with that in the blood, of course, because the combination with hemoglobin takes a longer time. The diffusion of volatile anesthesia is considered as carbon dioxide. Pulmonary diffusion capacity and carbon monoxide transfer test. It is a test utilizing the combination of carbon monoxide to hemoglobin, which is very speedy than oxygen. So we inspired around 0.1% of carbon monoxide because it's toxic through the alveoli. It speedy goes and combines with hemoglobin in the blood, so it doesn't give enough time for it to develop a tension in the blood. So we can consider that the perfusion of the blood at that point is not important, because the speed of the diffusion. You see, we can consider the tension in the blood is almost zero. So this test is used for the diffusion, not for the perfusion. Of course, it has been affected by disease as sarcoidosis and asbestosis and systemic lupus erythematosus, and whenever there is edema. Practical aspect of diffusion, we have hallucine, of course, when it diffused to the corrugated tubes. As we know, this is why we are nowadays tubes are made of silicon or polyvinyl chloride. And of course, we understand the decompression sickness, where nitrogen being diffused under high pressure to the tissue in a speedy way, and whenever the divers come out in a speedy way, the molecules come out in a speedy, blocking important structures. Of course, if we inspire carbon nitrous oxide salt 50% with a pressure of around 50 kilopascal, in an area where there is a nitrogen bubble, as we can see, of course, the less solubility of nitrogen in comparison to nitrous oxide makes the nitrous oxide goes through this area. Suppose it is a cyst or a pneumothorax, expanding it because it's more diffusible than nitrogen. Of course, it's important to utilize this idea whenever I anesthetize the patient for a graft of the ear, because a nitrous oxide, if it's used, it can expand and increase the pressure in the middle ear. Of course, nitrous oxide can escape and expand the cuff of the endotracheal tube. Of course, whenever the pressure is increased, it affects the tracheal mucosa. The effect of molecular size, of course, whenever we have a broken pipe, as we said before, and hydrogen is present, of course, it escapes and goes upwards because its density and molecular weight is small. On the other hand, if the ether bottle is broken and the molecules are spread, it spreads over the floor of the room, causing what we call the blue flame. Of course, it is heavier than hydrogen. This is why it's been spread slowly and to the bottom of the floor. So we can state that the second gas law is Graham's law, states that the rate of diffusion of a gas is inversely proportional to the square root of its molecular weight. It's not applied accurately with biological membrane. Of course, if there is a biological membrane, as in human beings, of course, we ought to think that oxygen would diffuse more than carbon dioxide, but it's not the case because we are discussing a biological membrane. But the Graham's law is applied on non-biological membrane. I'm sorry. Of course, can be applied, of course, to liquids. Of course, we ought to utilize it whenever we inject a local anesthetic to block a nerve. We must be close as much as we can to the nerve, because the slow spreading of the locals through this area being a solution. Of course, the spread of local anesthetics in the subarachnoid space is governed by the gravitational effects and the convection currents, and of course on the density of the local anesthetic. And these are the factors affecting the diffusion. Of course, we didn't mention before, of course, the membrane concerned. Osmosis simply, if we get a pot and we separate the pot by a semi-permeable membrane, which is very difficult to get from a solvent and a solution. A solution means that it is made of solid and solvent. So if we have a pot, as you can see, and we put both of them separated, of course, the molecules of solvent will spread according to fixed law to the concentration gradient to the right side, but it will come a point where it will be hindered by the presence of the solid. So the solid present here hinders the spread of the molecules or counterbalance the effect of fixed law. So if we measure the pressure at that point, if this is suppose and not, this is a closed compartment, so that if we have a manometer here or a monitor, it can estimate the pressure, the osmotic pressure of. If we don't have this upper one is closed, we can put a manometer measuring the osmotic pressure. This is how we do measure osmotic pressure of any solid. You see, suppose oncotic pressure, where we put the material in this area, and then we see how much it can counterbalance the effect of a solvent. If we have an area of this right side compartment is around 22.4 liter, and we put one solid of a material in this area, and we subject this area to 0 Celsius, this pressure yield will be 1 atmospheric pressure. This is the point we must utilize, and of course never forget that 22.4 liter. The sum of total molarities with the number of moles, whether it's moles or millimoles, would give the power of osmotic pressure. We call it osmolality. So molarity gives osmolarity. So when I talk about osmolarity, I consider it as the function of it as creating an osmotic pressure. We have here the total osmolarity of a Ringer lactate solution, which is considered around 300, and it's composed of, as we can see from all the particles. Of course, lactate here must be ionized to perform its capability as an osmolarity. Most of the osmotic pressure created in the plasma is due to electrolysis as sodium and bicarb and chloride. Of course, only 1% of all this is caused by albumin. Albumin mainly is the only, all the most important protein that creates an osmotic pressure, but it is a very in a low figure. But it's important in whenever we have a capillary loop, as you can see, Of course, the hydrostatic pressure is the pressure that tries to drive the liquid outside the capillary by the pressure of the blood pressure, which we consider around 7. But the oncotic pressure of the plasma present, which is at the artery, which is around 33.5. This difference makes the fluids come out from the capillary side to nourish the tissue. And then whenever we consider the venous side, we find that the pressure in it is around 0. So if we consider the 0 at that point, definitely the difference, the pressure will be capable of taking off all the fluids to the venous side. Osmolarity and the renal function, of course, simply speaking, as we said before, the osmolarity of the plasma is around 300 millimole milliosmole of liter. And then, as you can see, whenever the plasma is being infiltrated, of course, by the absorption, the millimoles is much more increased. Instead of 300 becomes 1,000. So this is about 3 times difference. Of course, when there is a difference in this figure, it denotes that whether, of course, if it's nearby, it could be due to diuresis. But if the difference is not as 1 to 4, it means that there is impairment in the renal function. Osmolarity refers, of course, we always talk about osmolarity, but osmolarity, which is a proper statement used, it is the osmol per kilogram of water of other solvent, which is preferred, of course, because of course we are talking here about volume as regarding osmolarity, which is affected, of course, by temperature, but osmolarity is not affected by temperature. Measurement of osmolarity, we have 2 types. Either we use the property of the material or the osmolarity of a solution in decreasing the freezing point. Of course, 1 mole of any substance added to 1 kilogram of water decreases the freezing point to 1.86. Imagine that. So this is why we use it. We throw salt on ice in Europe and in America. Of course, as we said before, the oncotic pressure is the pressure of the albumin, which is controlling the flow through the capillary loop. So the first point regarding the colligative property of solution, which is the properties of a solution as its osmolarity and capability to affect the osmotic pressure. We call it colligative properties, and we will discuss all these properties. First of all, its first thing is decreasing the freezing point, which we can use it to measure osmolarity. So osmolarity is the amount of the osmoles present, which creates the osmotic pressure. So in case if I want to measure the osmotic pressure, as we said before, we create the scenario where we put the solid where we want to know its osmotic pressure on the right side, and then we measure its pressure or its counterbalancing effect of preventing the spread of a solvent from the left side to the right. So the apparatus made of a steering probe, and there is a freezing cup, as we can see, where we put 2 millimeters, suppose, of urine, where we want to know its osmolarity number of osmoles in it or moles in it, which creates osmotic pressure in a refrigerating bath. Of course, we decrease this temperature to a level by steering, but to reach the temperature what we call supercooling. Supercooling is a state where the solution is beyond the freezing point, so it is not in a matter of freezing or a matter of freezing material. So we decrease the temperature, and then we begin to warm it till it reaches its freezing point, noted by, of course, this apparatus, which estimates immediately this change of temperature whenever freezing occurs and the cracks of the freezing materials appear. So this apparatus or monitor shifts immediately the change in temperature to osmolarity immediately. So this is the first method to measure the osmolarity. The second one is utilizing what we call the Rolls law. Rolls law means that if we put a solid as a solution this side and a solvent, and then the solvent begins to spread to the right side, the presence of solid in this area decreases the surface area for the solvent to evaporate, and hence it will decrease its boiling point. You see, so we are utilizing this apparatus instead of the other property of osmolarity is by decreasing the vapor pressure of the solvent by the presence of the solid. So the advantage of this one, that we can utilize very small amount of solution as sweat to measure disease as cystic fibrosis. Isotrope means two mixtures of solutions with each other by volume, and of course this mixture is based on their molecular weight and molality and so forth, to create and vapor pressure of both of them at a certain volume, So this is a combination of ether and halocene, and the other one is alcohol and water. Of course, alcohol, we never can increase the concentration of alcohol beyond the 69%, because water ought to be always 4%. Colligative properties of solution, as we said, is the character of it, this osmolarity of a solution, to decrease the freezing point, to decrease the boiling point, and the vapor pressure of the solid. All these are characters present called colligative properties, and these are some questions I figured it out in the exam. Wassalamu alaikum wa rahmatullah wa barakatuh.